Okay, shift gears here a little bit. Our material is going to change because basically, and you can see it here, is we're going to get into bonding. But before we get there, we've got to talk about electricity and magnetism and waves and whatnot. And this is going to get us to chemical bonding, which is basically what we just saw in the last chapter with the heats of reactions, right? The bonds were being broken, different elements were combining. Now we're going to look at those bonds. One more box. Okay, so we already covered in those first couple chapters how tiny all these particles are and how Avogadro's number, right? 6.022 times 10 to the 23rd. And it's and all those experiments that prove these things and whatnot, electrons, protons, and neutrons. All right, so our quantum mechanical model explains some behaviors that we're going to see, right? And we covered atoms versus ions, right? The electrons are moving, and this allows us to predict what atoms are going to react and behave in what way. Why some are metals here, for example, non-metals, why some gain and lose electrons. Like before, it was just the place on the periodic table, but now we'll look at why. Some elements are reactive and others are inert, and we'll see these trends on the periodic table. So if you have been, printed out and have a periodic table, be handy to grab it now, or if you watch this over again, or for Wednesdays. All right, so electrons have wave properties to them. So we need to talk a little bit about how light works and wave interactions. So light is the electromagnetic spectrum or the electromagnetic radiation. These are the same things, and it's composed of perpendicular oscillating waves. We'll see a picture of that. So one's electric and one's magnetic. And an electric field is a region where an electrically charged particle experiences force. So basically like magnets, right? And they're attracted to opposites. So a wave can move through all kinds of mediums. We usually only see, space and light and our atmosphere and water, but it's not exactly 3, it's like 2.99 something, but we'll just round it off. It's not that critical for us. So 3 times 10 to the 8th. And space is essentially a vacuum, right? And all light moves at this speed. It's a constant, and it's abbreviated with lowercase c. Okay, so maybe fireworks or thunder and lightning, you've ever noticed this. Right? Sound, the speed of sound is much slower than the speed of light. So you'll see the lightning flash or the firework go off, and then you'll hear the sound a bit later because they're moving at different speeds, quite a bit different. This would be, 3.4 times 10 to the 2 versus 3 times 10 to the 8th. So 6 orders of magnitude, which is basically a million. So light is about 1,000,000 times faster, if you will. All right, and this is, two-dimensional. Well, it's, on the screen. It's attempting to make it look three-dimensional, right? Where the blue is coming at you and then beyond the plane of the board behind and back and forth, whereas the red is in the plane of the board. And it doesn't matter which one's which. It's just that they're perpendicular to one another as the light travels. All right, so a few things to be on the same page of the ways that light is talked about. Amplitude, and this applies well when you're in a place like Hawaii. I assume everyone's been to the beach. Amplitude is the height of the wave. And we'll cover node to crest once we see it in a minute. And this, in terms of light, of visible light that you're used to, is the intensity of the light. right? Then there's the wavelength, and if you're into surfing or boating or etc., you'll already be familiar with this, and it's the distance covered by one whole oscillating cycle, so which is considered one wave. So the distance from any point on the wave, that equal full distance. So a crest to a crest, a trough to a trough, doesn't exactly matter where, just that you get to that same repeating spot on the wave. So here's the typical way we look at these things, right? The total distance divided by 2, or the 0 point to the top, is called the amplitude, and the wavelength is from any one point on the wave to that same full cycle, right? It's gone down and then all the way back up. So usually the easiest way to do this is measuring it from the top, or the crest of a wave to the next crest. Okay, so the frequency and the wavelength are in general the two most important things that we'll cover. And so the frequency is like it sounds, like the frequency of our class is twice a week. So the same thing with a wave. It's where you have some fixed location. And so how many times does the wave pass through that point in some given time? And so there's lots of different units for time, but we use, especially in, once you're beyond, physics, Newtonian physics of like a train traveling or something, where you can do miles per hour or whatever, we're always going to do everything here in seconds. And then since it's a wave traveling per time period, means you're dividing. So an inverse time, just like miles per hour, inverse seconds has this unit of hertz. This is what's commonly accepted and known. All right, so the energy is proportional to the amplitude and the frequency, which is the same thing as when you're at the beach, right? When you're at the beach and you go in the ocean, how much energy the waves, it costs you to fight through them or they hit you with, has to do with how tall they are and how often they hit you. Now, the waves in the ocean don't change wavelength by that great a deal like they do here in the electromagnetic spectrum, right? And you've been to the beach, so the larger the amplitude, the taller the wave, the more force it has. But more importantly, what we will care about is the frequency that the waves strike. So we'll see things with really high frequency can be quite damaging. Gamma rays most, but X-rays are probably what you have experience with. Right, so for waves traveling at the same speed, the shorter the wavelength, the more frequently they pass. They're closer together. This means that the wavelength and the frequency are inversely proportional, which we've seen before. Since the speed of light is constant, if we know the wavelength, we can find the frequency and vice versa, which is basically building us up to this expression you see here. A lot of times this is expressed where if you multiply both sides by the wavelength, that would cancel the wavelength on the right, and you'd have a wavelength over here. So wavelength times frequency equals the constant speed of light. And that's very similar to the dilution equation. Remember, m1 v1 equals m2 v2. Same thing with our ideal gas law, right? P v multiplied together equal to nRT. Whenever you have two things multiplied by each other, and just like the ideal gas law can equal a constant, the gas constant was in there, they're inversely proportional. So as one goes up, the other goes down. Okay, so simplest math, I think, from this chapter, and very similar to the dilution and ideal gas law, is you'll be given one thing and find the other, and then the speed of light is constant. Right, so you can get between frequency and wavelength back and forth, just depending on whatever you get. Nanometers, this lowercase n, this is the only time we'll use a different prefix than, milligram, for example, or kilogram. And that's because it makes nice units for light, and I'll explain more when we get to the whole spectrum. Okay, so here's more commonly the way it's written, right? Wavelength times frequency equals speed of light. We have two things multiplied by each other equal a constant. The c, 3 times 10 to the 8th, never changes. So if one goes up, the other goes down. Right, so they gave us the frequency, so we want to arrange like this equal to the wavelength. And then last, they wanted a, didn't really mention it here actually, but they're saying here, you know, like if it's, this would be if it said the units it wants, nanometers, which is just one last manipulation. Okay, so plug and chug, basically the per seconds cancel, that puts us in meters. And this is why we change things to nanometers. Is, I know this is times 10 to the 2 in scientific notation, but imagine it wasn't. It would be, move the decimal point over 1, 2. It would be 649. And this works out nicely for the units in nanometers of visible light. And we'll see this coming up in a minute. And visible light has a range of about 350 to 750 nanometers. So you have this range of about 300 units to talk about light, talk about color, which basically, if you've ever gone to the hardware store and bought paint, a lot of times they have a number that they go by, and it's a nice, you know, there's about 300 different colors. You know, you can blend them and like slightly different, etc. But okay. So then here's just going the other way. This is just in this example, right? And this is where not that many people listen to the radio anymore, but the number that you see on the dial is from the megahertz. So now we know the frequency. Again, we have to do a prefix change, but we can get to the wavelength by that same relationship, right? We need to account for this prefix change. Mega is 1,000,000, so 10 to the 6th, right? And then our ideal, or our speed of light constant. So change into normal hertz, get out of the mega. And then the speed of light. And so we get the wavelength of light for, you know, this radio station, 3 meters. And that makes sense once we see a little slide coming up that kind of puts in the range of all these types of light that you've seen. Okay, so color is kind of the most common way that people think when you say light. People think of these different colors of light more than the full spectrum, which we'll talk about, and you should know as a science major. All right, so white light has all of these colors. And in general, we've got, you know, 6 categories: red, orange, yellow, green, blue, black. When an object absorbs some of the wavelengths of white light while reflecting others, then it appears color. The observed color is predominantly the colors that are reflected. Okay, so again, we saw a bit of one of the lights, and it's about 350 to 750, but this is basically what visible light looks like, right? So the frequency and the wavelength both change, and so the color of the light changes as well, right? And then, as I mentioned before, the amplitude gives that brightness effect, just like the size of a wave at the beach. But we'll see that this isn't really our, you know, main interest. It's more the behavior of light, and then the different colors depending on your major and what you go do afterwards. Okay, so here's the full spectrum, right? And now when you look at the full spectrum, it's a pretty narrow window that visible light shows up, right? At about 750 to, you know, it has 400 in here, but it stretches a little bit. It's not a sharp definition. It doesn't just drop off the map like all visible light stops here. It goes out a few more wavelengths on each side. But what this does is when you put it in units of nanometers, it gives you a nice range to talk about a reasonable number And so a lot of, if you see in your biochem classes, there's a lot of times they would take a scan of a protein or enzyme, and then they would call it by the peak that it absorbs. So, like, for example, there's something called a P450 that chews up stuff that goes in your body, in your liver and your kidneys and stuff, and helps your body break down things that you eat and go into your body, and keeps your, like your garbage disposal, keeps your body healthy. And it absorbs, when they looked at it, it had a peak at 450, and so they called it that. Okay, so radio waves, we saw the meters of those, right? A microwave, we won't use too much. Infrared, if you've seen any infrared video of anything, this is also called night vision goggles. It's because the sun's on the other side of the earth and there's no visible light, right? And all these other lights are, all this light comes off the sun, but none of these are there anymore at nighttime. So infrared or night vision goggles take advantage and use the highest form of light that's still there. Excuse me. And so these are weaker in energy, right? And UV you've heard of, right? If you've ever had a sunburn, you put sunscreen on because the light is higher in energy and does more damage, right? If you've ever had an X-ray, they're trying to, it's higher energy. They should have put a lead blanket over you to protect you in your internal organs, because it can do damage. And then gamma rays, this takes about, I don't know, a few inches up to like a foot of concrete. It depends. It's just a measure of pure matter. So lead, for example, is really dense, and so that's why it gets used. But water can stop it too. You just need a lot more water. And then concrete is somewhere in between lead and water, for example. So it just takes more material to stop these. All right, and so the wavelength out here is long for these radio waves and gets shorter and shorter, right? And gamma is the shortest, and so the frequency does the opposite, right? So the gamma rays have the shortest wavelength, and that means they're the closest together, so they hit whatever with the highest frequency. And then as the wavelengths get longer and longer, less waves are going to, come in contact or absorb anything, right? Okay, and now I'm assuming everybody's seen rainbow before. A prism is the way this is done for instruments and whatnot. A lot of instruments work off light forms like this, and when you need a different wavelength, this is the way it's done, where you shine light through, and then you can use this type of technology to change what light. And here's the whole spectrum that we saw in the last slide. All right, so really it's a whole spectrum, right? The electromagnetic spectrum, the entire one. We're used to saying light, and laypersons, you just think of the visible light, but it's really everything, right? The shorter the wavelength means the higher the frequency, right? And we saw the sort of the two extremes, radio waves and gamma rays. Right, and I covered too, right? Visible light, you don't put sunscreen on at night, right? You don't put sunscreen on to protect yourself from your TV or your phone or your lights at your house, but you do for sunscreen for for UV, and then there's higher things like the X-ray and the gamma ray. And the reason they do this is has to do with the wavelength of the electrons that make the bonds, and the energy in the bonds versus the energy in these types of light. So here's that infrared, right? It's taking advantage of the highest form of light energy left, right? There's obviously, you don't get a sunburn at night because there's no UV, and then at night there's also no visible light. So it takes it, infrared is the next highest energy form there. We'll cover this in Chem 162 in a little bit more detail, but basically, if you've ever taken a magnifying glass, you can take the sunlight when you're outside and focus it down to a beam. And a lot of times, this is one of the ways they can attack cancer. So if you just have skin cancer, it's on the surface and you can just scrape or cut it off of the skin. But if it's internal, you either have to have surgery, or this is one of the options where you can get basically just like the magnifying glass. So this is, if you took 3 magnifying glasses at 3 different spots and triangulated them, you can probably get, say, a leaf or something like that. You can start a fire because you focus the energy from multiple sources. And you can do this with gamma rays. What they'll do is they'll give someone a solution, and we'll cover how that works, that can then image and see where a tumor is, and you can possibly triangulate. And so the beams coming through aren't terribly dangerous, but where they all 3 triangulate and meet at the tumor's location, then the energy gets amplified as they all meet there. So it's a way to avoid surgery for cancer treatment, actually cutting the patient open. All right, let's talk a little bit about how waves interact. So interference, there's 2 different types, constructive and destructive. So constructive means they're in phase and they build together. Destructive is out of phase. If you've ever jumped on a trampoline, you've experienced this, right? If you're jumping on a trampoline and a second person gets on and jumps with you, they can jump, and land first. And so the trampoline goes down, and then you come down and land quickly right after them. And then when they jump up, that extra energy gets constructively given to you, and you'll go and jump in the air higher than you would without them. And that's basically, a crude way of thinking about this interference of in phase, where magnitude, it makes it larger and magnifies the interaction. And here it's a wave. And so not, pretty obvious, destructive is out of phase, right? So if someone exact opposite jumped, the trampoline would be coming up as you're coming down, that type of thing. Okay, so if the waves are, in phase, they'll add together. And if they are exactly, this one's doing where they're exactly the same size and out of phase, they would cancel each other. And so you would see nothing. All right, the other way that waves can behave is diffraction. And so this is done with some sort of obstacle, barrier opening that's around the same size of the wave, its wavelength, and it bends. If you've seen this anytime you've driven, looked past, or gone on a boat in and out of a harbor, right? They have the harbor jetty walls, and that's to block the waves when there's big swells and to protect the boats that are inside. And there's always, you'll see the waves bend around the entrance, and it narrows the point. It kind of does the opposite of what we'll see, right? It's meant to stop the waves, whereas in our examples in here, we'll look at focusing and centering them. So, right, this is, we're getting into the way an electron behaves, is that particles don't diffract, but light does. So is an electron a particle, or is it light? And a lot of these little instruments, we'll see some cartoons of them coming up. They diffract light through a couple of slits, and that slit is about relative to the size of the wavelength, and it gives what's called this interference pattern. So In the ocean, this is what you've seen, right? Here's your harbor entrance, and it doesn't stop the wave completely, right? But it blocks a lot of it, and then it'll wrap around. In some places, some harbors will have like a second jetty here where you actually kind of, snake in around them. But it doesn't stop the waves completely, right? You've seen it hit and wrap and diffract. Right. So waves do this, particles don't. So, imagine a gun, or if you were throwing baseballs at some barrier like this, they move straight through. There's no diffraction when it's a particle. Okay, so this is one of the ways that they could determine the wavelengths a long time ago, 100 more years, is they would take some light source and make these slits, and then you would see these patterns here where the waves constructively and destructively, right? So you get this light and dark patterns, and they can play with the slit size, and move the light source closer or further away, and study these things. Okay, there's something called the photoelectric effect. And what this is it's a behavior of metals where they'll emit electrons when you shine a light on their surface. Right, so typical wave theory, this effect of the light being transferred to the electron, basically. So according to this idea, if the wavelength of light is made shorter, or the light waves, the intensity made brighter, more electrons should be ejected. And one of the ways you've kind of seen this, maybe you see it in the like really old movies, or really old people, maybe your grandparents, where people before sunscreen and skin cancer worries in like the 80s, older people, older now, but whatever then, would go to the beach and oil up, and they would take aluminum and angle it so they could get more light and reflect it from multiple angles onto their bodies. You don't really see people do that anymore with the incidence of skin cancer. Okay, so the energy of waves still proportional to its amplitude and its frequency. So if you had a dim light, there would be sort of this lag time on the electrons, and this will make more sense coming up. But here's basically the idea, right? You've seen metal surfaces are shiny, the light can will shine off of it. And what we're looking at here is the way they started to discover these things after the Industrial Revolution, when there's electricity and there's vacuum pumps. You'll have this voltmeter, you hook up some battery, voltage source. You got your two terminals, and this needs to be in a perfect vacuum so that when the electron comes off, it doesn't go onto gas molecules, which this is basically the reason, if you've ever been in the desert, it doesn't really happen too much in Hawaii because there's too much moisture here, but in places with really, really low humidity in the desert, you can rub your feet together and build up a static charge, and that shocks someone. But anyway, so what they're doing here is learning about light, and if you hit this piece of metal with enough energy, you could get this electron to jump off. The current wants to make it go, but it's still got to make the jump, and then your meter tells you the energy associated with that. So sort of as usual with these things, there's always a little problem, or the examples a little too simple. And so there's something called the threshold frequency, which is regardless of intensity. So they do these experiments, and they observed that there was a maximum wavelength that was needed. And then also that a high frequency of light, this we already saw this a little bit with the dim source, caused electron emission without any lag time, which I think that'll make sense in a minute coming up. So this is all just building up to basically electron behavior. Again, you saw like on the last exam, it's not a history class, so you don't need to know which scientist went with which subject. If you're a chem or a physics major, you'll see these things again, especially physics. You need to know who did what. Um, anyway, so Einstein basically started to notice that light came sort of in these packets, and they called them photons. So there was a certain amount of them, and the energy of a photon was proportional to its frequency. And we know that the frequency is proportional to the speed of light. And since the speed of light is constant, these things are our previous equation, and this one then must be related. And so, again, it's not a history class, but Planck is just another famous physicist. And here's the value that's called Planck's constant. And you can tell we're dealing with energy because here's joules, and then it's joules a second, because we're going to multiply it by the frequency, and the seconds will then cancel because frequency is inverse seconds, and we'll be left with energy in the form of joules. And notice this is a really small number, right? Because electrons and all these things, right? A mole is 6.02 times 10 to the 23rd. So the energy is really small for these individuals. Right? And so here it is into our previous equation. There's the frequency, HV. And so a lot of times in future science classes, not just chemistry, you might see HV written somewhere. And what it means is that you need energy in the form of light to accomplish whatever it is that's going on. Okay, so all this is telling us the energy is equal to Planck's constant times the frequency, and we know from the speed of light and the wavelength relationship, you can plug in and express frequency as c over wavelength, or this is called lambda. Okay, so pretty similar to the last one. It's another plug and chug. This one calculated with photons and laser pulse with 337 nanometers and total energy. So it gave us two of the pieces of information. We're going to plug it into our new equation. We've got our nanometers we need to get out of. Then this one wants millijoules, right? Just, milli and kilo are the common ones in the world of chemistry. The only time we use nano is here with light. And then this is saying a laser pulse and how many photons that makes. So the photon this is sort of like, at a carnival, or they have these in bars now, where if you punch the bag, it tells you, your ranking or your energy or something. So our new equation here, just tells us how much energy that wavelength gives us for one photon at that wavelength. And then now we're going to find out in this laser flash how many photons are in that pulse, that flash of light. Okay, so from the wavelength in nanometers, let's get out of nanometers, right? Because we need it in nanometer meters to cancel out, and with Planck's constant correctly to cancel the meters in the speed of light. So the meters cancel. Now the inverse seconds, right, in meters per second cancels with the seconds in Planck's constant, and we're left over with joules. So this is how much energy each, like single punch at the machine, each single wavelength or, photon really delivers. And the total, okay, then it wanted it in millijoules for whatever reason. So we're in joules, and millijoules don't work, so we need to get in the same. They gave it to us in millijoules, so we need to move the decimal point over 3 spots. And then that was the total. This is how much each photon delivered. So that must mean that there's this many photons in that pulse. However long the pulse is, like that's not clear from this. The pulse could have been a second or 2 minutes, who knows. So most of these are kind of just making sure your units cancel, right? I know they're new units. So let's do another one. Usually whatever they gave you in these examples, the first time we work through and do it the opposite way in the second. So last time it gave us what, wavelength? This one is asking for frequency. But remember, wavelength and frequency, if you're given one, you know the other. Okay, so frequency of radiation required to supply 1 times 10 to the 2, so 100 joules of energy from 8.5 times 10 to the 27 photons. So we know that we have this much energy, and this is how many photons. And we're trying to figure out, let's say if you had a laser, what wavelength or frequency, since they're related, you'd have to set it to. All right, so from the total energy, we divide that by the number of photons. That tells us how much per photon. We use our new equation to solve for V, so that's just Planck's constant. Right, so that 100 joules divided by the amount for 1 photon tells us how much energy per photon. And then just Planck's constant, rearrange our equation, and this would tell you what setting you would need. Usually these settings are in wavelength, not in frequency, but it's still, one more calculation, but the value doesn't change. It's just sort of a different way of looking at it. And depending on what labs you have, but often there'll be a wavelength tuner, and sometimes in freshman chem. I know at Manoa we did this, but it wasn't until Chem 162. Okay, and noticeably it's mostly just units canceling, right? Inverse seconds is hertz, and that's the units for frequency. All right, that ejected electron from the photoelectric effect that we saw there, and that mentioned that threshold frequency. And so we've gone through and covered how the energy comes in photons, and the amount of energy is a function of that frequency. So if you're shining the light on a piece of metal, there's got to be some minimum energy that's needed, and then above that is extra light, but you need that to get it out. Right, so higher frequencies, the electron absorbs more energy than is necessary to escape. The excess energy becomes kinetic energy of the ejected electron. The analogy that I like for this is, imagine you're on the ground floor and your friend is standing on the roof of some building, and you're going to throw a baseball to him. Right, so the binding energy would be the altitude, the number of feet, the elevation of the roof. Right, and you throw the energy. If you do just the right amount of energy, then they catch it perfectly right there at the top of the roof. If you throw it a lot harder, then it goes flying over and past your friend, and maybe you could throw it to a building that's 5 stories tall or 10 stories tall, but the baseball goes flying past the top of the roof and keeps going. Okay, so spectras are commonly, that's the common term for what we see. So when atoms, and basically this is getting to the concept of first probably fireworks, but when atoms, or more likely molecules, absorb energy, that energy is often released in the form of light. So fireworks, neon light do this. When the light is passed through a prism, then the pattern seen is unique to that type of atom or molecule. So when you see neon lights, they can make them look different colors by different mixtures of gases that are in there. Right, and this pattern is called an emission spectrum. Emission because it's coming off, and spectra because it's a blend of wavelengths of light. And so you can use this to identify materials. It's kind of like a fingerprint, right? Every atom gives off a unique set of wavelengths of light. And at Manoa, we used to do this flame test, but you need gas and kind of, Bunsen burner and kind of a little bit of a rare setup. But once again, I know this is a physics and sort of name heavy chapter, but again, it's not a history class. So Rydberg, another famous physicist, whenever scientists observe when they were studying things, they always start off with the simplest thing, right? Hydrogen is the lowest weight, the least number of protons and electrons, and so it's the easiest thing to study. And so doing all this stuff, he saw this inverse square relationship. So 1 over the wavelength of light that you're using, you would see this 1 over n, and n1 and n2 are just whole digit integer numbers, right? And so inverse means on the bottom and square. Okay, and so they had these different lamps, and at Manoa we had, I think, a hydrogen and a mercury one. And basically what it is you've got an electrical source, you've got a vacuum where just that sample is in there, so hydrogen gas. And when you turn on, the power source, you have electricity flowing through it, and then it emits and comes off. So when it comes off, it looks like, this one's whatever, reddish, pinkish, right? Then you need a barrier to focus and make it into a beam, like a laser pointer does. Right, then if you want to tell what the different wavelengths are in, you need a prism to split it up. And we see that the pink blended that you see is really a combination of these reds, blues, and violets. And these distances between them can relate directly to energy, right? So when we looked at the form, at the whole spectrum, we saw that the difference in the wavelengths of light reflected right on one side was infrared, which was weaker, night vision goggles, then to UV on the other side that you needed sunscreen that did damage to biological molecules. It has to do with the energy associated in the bonds. All right, so you can do this with different gases, right? And we call these neon signs, but they're not all just neon in there. They can put a blend of different things in there. So there's mercury and helium and hydrogen. And so the way that you can have a mercury one is that it's not, right? Mercury is actually a liquid, but if you have it under vacuum and only have a small amount in there, then you'll have some mercury in the gas phase. And so what this tells us is that every element has a unique spectrum, and the spectrums are the simplest because they're simplest for the lighter elements like hydrogen and helium are the two lightest, because they have the least number of electrons, and the electrons are what we're talking about here, these excitation of electrons. And when the electrons drop back down, they emit that energy in the form of light. So this, for example, bullet manufacturers, when they make a batch of bullets, they spike each batch of bullets with little small percentages of different metals. So bullets are almost all there. It's 99% lead, right? Lead is a very heavy, cheap element. It's not really useful for too many things. We use it to, like when you get an X-ray, they put the lead blanket over you, right? They're used in guns. We shoot them, in wars, and police officers have them, et cetera, and no one goes around picking up the bullets and searching for every bullet. But at a crime scene, They do. They'll examine the gun and they'll examine the bullets. And the companies that make the bullets know that they're going to be used, and you can mix in slight percentages of different elements, and it gives it a unique fingerprint. So if you commit a crime, if someone commits a crime, they find a bullet on video or in your possession, and they match that to the crime scene, or they pull, if you shoot someone, they pull it out of the victim, and then at your house they find the same batch of bullets. And the companies that make the bullets take this type of spectrum before they sell them. Then they ask the company, on the box for it, your fingerprints are on the box, et cetera, et cetera. This is how they connect the dots and prove this type of thing. And so this is what it would look like if your lab, if you were doing it. These, of course, are the better pictures. So, and this lasts very briefly. So what we would do at Manoa is you have the Bunsen burner, you have a liquid solution where you put, a paper clip, dip it in the solution, you let it dry a little bit, and then put it into the flame. And very briefly, for about a second, you will see the energy from the burning hot Bunsen burner is enough to excite the electrons. And then when they drop back down, you see that spectra, and the different elements have this fingerprint. Now, this is just the crude one with your eye, which is this, right? It's not the individual ones. You need a prism to separate them out, right? So, sodium, potassium, lithium, barium, and they all look a little different, but this is just the qualitative to the eye look. It's not the quantitative by the wavelength energies and fingerprint. Okay, so what an element emits is just the opposite of what it absorbs. And that's what this is trying to show you, right? So the one is light going in and one is light going out. And so they're opposites of one another. Not too terribly important for our class, but physics, engineering people, you might see this again. Okay, I know I've said it before, say it again. It's not a history class, so you don't need to know everyone's name, but Bohr is another famous physicist. Well, we got his first name here. Niels Bohr basically proposed this idea that the electrons could only have these specific amounts of energy, so they were quantized. The electrons traveled in these orbits, and they were a fixed distance from the nucleus. Basically, you can think about this like the way electrons move, the way planets move around our sun. So there are these sort of stationary places that they're at. And so if they're stationary in these sort of orbits, like planets around the sun, then the energy of the electron was proportional to that distance of the orbit, and that would explain the wavelengths of light. So that emission spectra, the emitted radiation, basically what they're doing is they're jumping between the orbits because the orbits have different energies. And so the distance between those is what the wavelength of light that you would observe. So sounds kind of complicated, but here is that n from Rydberg's equation and constant. And now this looks more like, down here at the nucleus is the sun, right? There's Mercury, then Venus, then we're the third planet, right? Earth, Mars, Jupiter, etc. And when the closer you are, the moving down means the energy comes off. So sort of what you saw in the neon lights there and the spectrum was either electricity or the intense heat from that flame was enough energy to push the electrons up, and then when they dropped back down, that's those wavelengths of light that you saw. So these lights that you see coming off here are supposed to be these wavelengths of light, and so notice the distance between them, right? They're different. And that's because these distances between the orbits are different as well, right? And the shorter the wavelength, the higher the energy. So the bigger the gap, from 5 down to 2 gives us a higher energy and a different color, right? And as the wavelength got longer, the energy was less. So 5 to 2, 4 to 2 versus 3 to 2 should be less energy. Wow, I haven't taught this in a while. I forgot all the names that were in here. So once again, not a history class. De Broglie is his name, another famous physicist. Basically came up with the idea that particles could have wave-like character, which is what electrons are. So since they're so small, the wave character of electrons, it's significant. And so you can make these beams of electrons, the same type of things with these slits like we did for waves for typical light, but you can do these for electrons. And what they observed is the electron had that interference, which means it has to have wave behavior. And this is where, if you've heard it before, wave particle duality, which is extremely rare, and basically, for all we care about is in electrons. Okay, so H, again, Planck's constant, there's our wavelength. And then if it's a particle, it has to have some mass, right? And velocity is the speed, which is energy, pretty similar to momentum. And so this is what they saw when they could have their electron particles. And so if the electrons behave like particles, there should be just 2 bright spots, right? Like if it was just a baseball, it would just pass through and hit the two spots. But what they saw when they set up these, or he saw, when you have your barrier, you set up your 2 slits, you have your electron source, you got the typical wave interference, constructive and destructive. So this told them that electrons have this interference pattern, which means they have wave-like features. Okay, so here is clearly using our new equation. It gave us the speed, so we're basically just going to plug and chug. This is given, this is a constant, the mass of an electron. That's sort of the one thing that's missing from the title here. This one. But then we would use everything we were given, right? So our normal H, Planck's constant, there's our wavelength, the mass is a constant. So there's really just 2 things in here, right? The wavelength and then the speed. So this one gave us the speed, which means we're going to solve for the wavelength. So plug and chug, but units canceling. And you can see we're in this chapter. You want to get good at the scientific notation on your calculator and be comfortable with it. And then here's where, if you want, you can put this into nanometers, but that's really only for visible light, right? And so all of our units here are going to cancel out. Right there goes for kilograms, meters, seconds. And then this must be the opposite. What was the last one? Oh no, same wavelength. So this is the same math, just with a different speed. So the same plug and chug. Basically all the same math, right? We just moved, we needed to go to kilograms from grams, but all the same math. So those 2 are basically identical, just a different number. This light grams to kilograms. Okay, complementary properties. So this wave particle duality has a little issue with it where when you try to observe the wave nature of the electron, you can't observe the particle nature and vice versa. So the more you know about one feature, the less you know about the other. So the wave nature has this interference pattern. The particle one has sort of positioning, like more like a baseball versus just a sound or light wave. And so these are complementary, which means related but opposite. So again, the more you know about one, the less you know about the other. More physics names, Heisenberg, you've probably heard from that show Breaking Bad, which is kind of ironic that he called himself that because it's really a physicist, not a chemist. And in the complementary sense of the electron motion, it's this uncertainty principle. So basically the idea is that the product of the uncertainties in both the position and the speed is inversely proportional to its mass. And so what this means is the more you know about the position of a particle, let's say an electron, the less you know about its speed. The more you know about its speed, the less you know about the position. We're not going to use this equation. There won't be a problem on the test. It's just, again, it's not a history class, but if you're a physics major, you'll want to know whose principle was with what theory and whatnot, but not on our exam. So again, more of, the particle versus wave. So any experiment designed to observe the electron results in detection of single electron particle and no interference pattern. And this is building us up to the way electrons move in the atom, right? Classic physics means Newtonian physics. Particles move in some path that's their speed, right? The position and then whatever act is forcing on it. So this is, if you run around a track. Right? And so you know where it's going, you can predict it, right? When a train leaves Detroit headed towards Chicago and you know the distance and then how many miles an hour, you can predict what time it's going to leave Detroit and get to Chicago. But since with an electron, you can't know both the position and the velocity, that means you can't predict the path that it's going to follow for sure. So it has this indeterminacy. You can only predict a probability. Right. So the best you can do is describe the probability of an electron will be found in some region using statistical functions, which is way too high math for us. And the way they relate this is here with baseball, right? And so you can predict where the ball is going to go because you know how you threw it and the speed and where it started and where it's going. But what we learned in the world here of electrons, because they're so light and they're moving so fast that it has this wave particle duality, and in quantum mechanics, instead you get this probability distribution. Right, and so what this symbol is here is called a wave function, which you'll cover in physics. This equation is not going to be on our exam at all. If you've already had physics, you've probably seen this before, where this is basically just momentum, right? Kinetic energy is something in motion, 1/2 mv squared. And we saw this same thing when we talked about the motion, diffusion and diffusion of gases. So an electron with some given energy, the best you can do is describe the region that the atom, high probability of finding it. And we call that and orbit. So very similar to the way planets go around the sun is the way we're going to think of and talk about electrons going around the nucleus. And so we'll have this distribution of probability of where that electron's going to be. And so the properties of different atoms relate to the energies of its electrons, which are in these orbitals. So again, this symbol is called a wave function. Won't be on our exam, that previous equation. And I'm not even big on you memorizing these names. I'm not going to test you on the actual names of these things, but there's 4 quantum numbers. We're going to cover 3 here. The principal quantum number is that integer n we already saw, and that's the orbit around the sun. Like Mercury is the first planet going around the sun, so its value is 1. Right? Venus is the second, its integer value, so 2. Earth 3, etc. Angular momentum quantum number is denoted L, magnetic quantum number M sub L. I won't be testing on you on memorizing, right? You saw in the last exam, it's not a vocabulary test, it's not a history test. This is just telling you, what these numbers, how they're symbolized. All right, so this takes us back to the Bohr's model, where the n can be any integer. We start with 1, again, Mercury the closest to the sun, then 2, 3, 4. The larger the value of the n, the more energy the orbital has. And we saw that when we looked at the electrons that were going from a higher level down to a lower one in the light that came off. All right, so an electron would have no energy when it escapes the atom. And so these are basically assigned as being negative. And that's why you see the minus sign here. So just sort of explaining the equation. The larger the value of n, the larger the orbital, right? N equals 1, 2, 3, 4, 5. So for a hydrogen is the simplest case, right? All this stuff is always based off hydrogen because it's the simplest element, right? 1 proton, 1 electron. And that's the easiest thing to study. And again, at the time that this was going on was the Industrial Revolution, where we were getting electricity and vacuum pumps, and you could do these things. All right, so as n gets larger, the amount of energy between the orbitals gets smaller, which was by the relationship n squared. Let me see what the next. So this isn't drawn to scale, right? It's 1 over n squared, and these should get much closer, right? It's difficult to show that on the proper scale. And the 4, 3, 2, 1, this looks like the jumps that we saw, again, not drawn to scale. We'll go back. That we saw here. Right, so I know I'm going a little fast, but I think it's important to connect these two while we're on it on the same day. So, right, here's N5 dropping down to 2, and we see a lower, smaller wavelength, thus higher energy light coming off, versus N4 to 2 and 3 to 2, and you see these different wavelengths of light. And then here are the actual energies associated with those. You can calculate them. This is just for hydrogen, the simplest case. So we could go back to those ones, 4, and they were to 2, but you could have 4 to 1 in theory, and 3 to 1, and 4 to 2, 3 to 2. There's obviously lots of different options. Okay, so transitions then, in order to transition from an higher energy state, the electron must gain the correct amount of energy. corresponding to the difference in energy between the final and initial states, which is basically just kind of, imagine these are floors on a building, and if you're throwing a baseball up, you have to have enough energy, right? If you throw, from the first floor to the second floor, if you throw a baseball up and you don't have enough energy to reach the third, it's going to land on the second. Except here, you don't the light is the energy that comes off or goes in, it needs to be exactly that distance, right? And so here's where we saw before. The idea here is, you have a firework go off in the initial explosion or in the flame test. The Bunsen burner provides enough energy to bump the electron up. And then when the electron drops back down, this is that wavelength of light. And we saw in the hydrogen one, the differences in those gave off different forms of light associated by that 1n² values we saw on the last slide. Okay, electrons in higher energy states are unstable and tend to lose energy and transition to lower ones. The other way to think about this is sort of like Connect 4, if you've ever played that game, right? So if there's an empty spot, an electron in a higher energy isn't going to stay here, and it's going to drop down to a lower one. And so this is that emission spectrum, and it corresponds to the differences in the energy states by that 1/n² value. So hydrogen, again, is the simplest situation. And so we combine all these things we've talked about here, right? The wavelengths and the emission spectra are, they always start with hydrogen. You can predict by calculating the energy between any two states. So we had our energy for the states, and our final and initial are the difference between the two. And the photon is the light that we see coming off, and that has to be the opposite, right? The light, if the light's coming off, that means it's released by the hydrogen, and that's the difference in the two states, right? And so here's our photon equation with our 1/n², and 2.18 is directly to a hydrogen atom. And so here's the picture of this, right? So this would be, you have a hydrogen atom, and if you pump enough electrons in it in, say, a hydrogen lamp, or a quote unquote neon sign, but it has hydrogen in it, if the electrical energy is enough to bump the electrons up to these higher ones, the only ones we see are the transitions, are the ones that give off wavelengths of light where our eyes can see, right? And all we see is visible light. So a tanning bed essentially is this type of interaction where you have a light in there. It uses electricity to bump the electrons up, and then when they drop down, a tanning bed gives off UV light, which is higher energy, so a bigger gap than visible. And infrareds, this is how the infrared goggles work, is they're looking at these transitions that are still happening when there's no more visible or UV or any higher light around. And so this is what we saw on the previous slides, but now with an actual wavelength in there. So when a firework goes off, there's certainly heat up there, but it's in the sky. We don't feel it as far away. And this is all we see from the ground as the fireworks go off, is the combination of different elements and different lights. And again, in a lab, you can do the fingerprint pattern that I was talking about bullet makers do to give a fingerprint to the different bullets. Okay, so let's do a couple sample problems. Calculate the wavelength of light emitted from hydrogen, transition 6 to 5. So again, it's pretty plug and chug, right? It's just all these new equations. So I know it might seem like a bit, that's that Rydberg constant for one energy level. And then, the energy of the atom is, we see that in the photon of light. So these are equal to each other. They're just in, opposite, positive, negative values, leaving one, going to the other, kind of like the endothermic and exothermic. And then once we know the energy, that we combine it with the last equations we did, we can get to the wavelength of light. And this is what your eye sees. So if we're going from 5 to 6, right, there's our ends. This tells us the energy that it's going to take. Right, from 6 to 5 means it comes off, and we'll see that in the form of that wavelength. So the difference between those gets us to that energy. That energy correlates specifically to some wavelength. Then here, if you wanted to put in nanometers, you could get it and see if it's in the form of visible light. But this one would be 6 to 5, which we saw on the last slide. Would be, well, it'd be off the screen, but you can see here it's showing 5 to 3, and 4 to 3 was infrared. So 6 to 5 is going to be above infrared and not visible light, obviously. So you wouldn't see this with your eye anyway. Same calculation here. It's just doing 2 to 1. So I'm not going to go through it, go through it much faster, because the only thing different here is 1 to 2. Right, and now we get a much more, this is going to be much more powerful because it's the squared value between it. Right, and the wavelength is in that UV region, right? And 3 to 2 we saw on the last slide was in the visible. So keep in mind, go back, it's a squared, and this is trying to, but it's not drawn to scale, right? Because the squared would be 1/4, then 1/9, 1/16, 1/25. So these should get really much closer together. It's difficult to scale that on a slide here, on a picture, and have it truly drawn to scale. But the last one, sorry, while we're here, 1 to 2. So we see here, right, there's or 2 to 1. That it told us it's UV light, right? And you can see, again, not really the scale, but the gap here is much, much bigger, which means it's going to be higher energy light. Okay, I think that's a good place to stop. We sort of jump and talk about sort of the movement of the electrons here. So it's related, but I feel like I went kind of fast, and it is a bit of math that's just plug and chug, and there won't be too many of these on the exam, and they'll be simple, pretty plug and chug ones, because this is really heavy physics. Just to get to this last part here is what we care about for future chemistry behavior and the way the bonds come together. So this is sort of a good transitioning slide, where everything above this is just getting you to believe in wave particle duality and that electrons are moving, and physics and chemistry overlap a bit, but we won't be doing that much math like that in the coming chapters, because electrons, we're going to look at how they spatially move, and we won't care about their speed or the mass or the wave portion of it. But wave particle duality is a big important thing that explains the way the electrons behave, which electrons are what make the bonds. Okay, and we're out of time, so obviously I'll be stopping there. Okay, Nick, I just saw your message. The chat box was off the screen. Solar charging. So we need to do. We can talk about solar energy and how it works, but we need a little bit more chemical bonding and stuff. But basically, pretty similar is what light does. Solar panel is it pushes. You get an electron that jumps from one level up to the other and creates energy, right? And you can feel the sun. It can burn your skin, and you can feel the warmth of it. But we need to talk a little bit more about chemical bonding and metals, and that's, solar panels are basically made up of silicone, and it's a uniform made substance, which, I don't know. When we get more finished with the chapter on bonding, it'll be a little more clear. There's a few slides, right? Because chemistry and engineering overlap, and there's a couple slides that deal with the issues of where the two intersect. And we saw that a little bit when we talked about the periodic table. Right, and group 4, the top of group 4 element is carbon, and then you move to silicon and on down, and lead was at the bottom, right? And lead is very different from carbon, right? Carbon is charcoal and that you cook with, and the pencil lead is carbon, and that's very different from the metal in a pot or a pan or a bullet. And we'll see it's those key features, but they're bonding features that make them so useful in electronics, and solar charging is one of those things. Okay, it's tough to talk for an hour and 15 minutes straight, but I did it once again. So I know that was a lot of stuff to cover. Again, the problems will kind of be plug and chug. We'll put a few of those, but I'm not going to put one of every problem that we saw here on the test, or on this in this slide on the test. We'll see that it's mostly conceptual after this. So, okay, I'll stop talking and feel free to hang out. If you want to questions, comments, thoughts, theories, you can unmute, hit the button, or if you've got, take off if you've got a class to run to, etc. And we'll pick up here on Wednesday.
Thank you, Professor.
Yeah, no worries. Have a good day.
You too. Bye-bye.
Bye. Stop.